Okay, I'm super excited today. We're going to be looking at where those arrow diagrams come from. We're going to be using the projection operator, and then we're also going to apply it to MO theory and look at where the molecular orbitals come from. So we're going to show that this projection operator allows us to create the molecular vibrations and molecular orbitals. So last time we did the reducible representation and we decomposed it into the number and types of irreducible representations that we had. We looked at, for water, these three translations, took up one of the A1s, one of the B1s, and one of the B2s. The rotations gave us an A2, a B1, and a B2. And so whatever was left over were the vibrations. So we had, yes? Yeah, so we had two A1s left over and we had a B1 left over. Then we had three vibrations and we had three symmetry types that are going to be associated with those vibrations. And we understood what translation looks like. They're all going in one direction. Rotation is rotating around an axis. But how do we reveal what the vibrations look like? So this is what we use the projection operator for. So we know those translations are going along any one of the axes, X, Y, or Z. The rotations are rotating around those axes. We have the vibrations, and so where do these arrow diagrams come from? We can use the projection operator to come up with these arrow diagrams. So this was my first understanding back when we were doing, even in high school or maybe even middle school geometry. We were looking at the angle of like a cannonball being shot out, and you have the angle of elevation. And then you have a Y component and an X component. And they talked about it being a projection. Like if you took the hypotenuse and you put a light above it, it would cast a shadow. Okay, and that would be the cosine of that angle. And that the shadow cast forward would be the sine of that angle. And so this idea of light and shadows are what we mean by projections. So we're projecting onto a different coordinate. And so that's what we're doing with this projection operator. It's useful for making these SALCs. So that's an important acronym for you. Symmetry Adapted Linear Combinations. Now, most of the time, this SALC is coupled with MO for molecular orbital. But these are symmetry adapted linear combinations of atomic orbitals to make molecular orbitals. They could also be combinations of vibrational wave functions too. So SALC can apply to vibrational wave functions and it can apply to atomic orbitals and give us molecular orbitals. And we'll do both today. Hopefully there's enough time to get through both. So this is what I mean by projection operator. Think about the projector in the room. We have a light source and we have an imaging element, and then we have the screen which has the image on it. So this image is coming from the imaging element coupled with the light source. And so what are we going to do for our situation? Our source, the imaging element and the image, using this projection operator, are a particular understanding of something related to the molecule. So we're going to take this OH stretch, just one of them. Just pick a bond, and we're going to say, if that bond stretches, let's run that through this imaging element, which is known as the character table. So the character table is our imaging element. And it will take the source, this OH vibration, and turn it into this arrow diagram. Okay, so we take the source, we pick a particular bond stretch or bond angle change, or in atomic orbitals, we pick a 1s orbital, and then we run it through the character table, and that produces an image. And that image is the symmetry adapted combination of all of the bond lengths that are joined by symmetry in certain ways. And so it's really pretty cool. I think this is a fantastic thing that shows the power of the character table, which relies on the point group, which relies on the structure. So if you can't draw structures and get the point groups, all of this is garbage. So you got to get the correct point group, and then you can understand the symmetry of the molecule. So let's look at this projection operator for vibrations. So we have this C2V character table for water, And our source is the same in all of these cases. It's just that OH stretch on the left side of the molecule. And we're going to go through all 4 rows of the character table. Now, this would be quite cumbersome for benzene, but you could do it for benzene. You know, it's just more stuff to do, okay? But we're going to do with water. There's only 2 bonds and an angle, and there's only 4 rows of the character table. So this is something we can get through. So if I take this stretch and I do an E operation on it, nothing happens, right? Nothing changes. So that's what my image looks like. So this imaging element is going to give me that unchanged picture using the E part of the image generator, the projection operator. If I do a C2 on it, okay, it's going to switch over to that other bond. You see where the arrows went? And it's a +1. So the arrows don't change direction. If it were a -1, the arrows would change direction. Okay. And then I do a reflection in the XZ plane, which is the one coming out of the board. And so they swap over to the other side. And then the YZ is the plane of the board, and they stay where they are. Now, what I do is I combine all of these. So notice these down arrows match. And so if I were to do like vector addition on this, I would add another arrow there. Up here, I would go this way, right? And so I've added this arrow and added this arrow. Then I come over here and I add an arrow on this side. Okay, and I add another arrow on this side. And then over here, I add another arrow on this side. And let's see, I've got 2 over here actually. Yeah. And so those are all of the arrows. So notice these arrows, nothing is canceled, right? So the result of vector addition, I go from head to tail of both of them. And the result of this vector addition, I go from the tail of the beginning all the way to the head of the end. And so I have an up arrow on my oxygen, and I have 2 down arrows on my hydrogens, and that's what I end up with.
So essentially the vector addition, you're just stacking everything on top.
Yeah, head to tail, head to tail. Keep the angles the same and just translate the arrows. So you translate the arrows head to tail, and then the result is from the original tail to the resulting head. Isn't that nice? This is my arrow diagram for the A1 vibration. That's cool. Okay. Does that make sense? Okay, now let's do one that's A2. Okay. So I still the E gives me the same picture. The C2 gives me the same picture, but it's on the other bond. And then the -1 under this, we have a reflection which moves the arrows, and the -1 changes their direction. And then this one stays put on the first OH bond, but the -1 makes them change direction. Now I go ahead and do my vector addition. I have this arrow, and then this one over here is in the opposite direction. And so head to tail, it doesn't move. Yeah, and so then this one, it goes up, and then it goes left, and then it goes back down, and then it goes back down. So head to tail, it doesn't move. And then this one, it goes out from the C2 column, and then when it gets to the 3rd column, it comes back. So it doesn't move. And so the result of this is no movement at all. So this tells me there is no vibration under A2. I knew that from the previous thing, A2 was 0. But this, even if I did the projection operator through that imaging element of the character table, I wouldn't have a vibration associated with it. That's really cool. Yeah. Let's do the B1. So now we have a different row here. So the E is going to be the same. We have a -1 on the C2, so we have the swapping of the arrows. They move to the other bond, and they're changed direction. Here, they're moved to the other bond, but they keep the same direction because this is a plus here. And then here, they stay put, but they change direction. And so once again, I have a down arrow and an up arrow, so that's canceled. I have an up arrow from the C2 and a down arrow from the sigma. And then this one goes over and down, and then back up, and then back over. And so this one is all of them are going to cancel out, and I have no motion. So there's no B1 vibration. Okay, so E is the same. We move it to the C2. We have a -1, so they change direction. A -1 on the reflection, so they change direction. And then a +1 on the first reflection, and they stay put. And so here we have a couple of down arrows on this one, the first and fourth column, and we have a couple of up arrows here, the second and third column. And then this oxygen goes up and down, and then down again, and then up again. And I've exaggerated the lengths of these arrows. The oxygen really doesn't move that much, but it gives us the correct picture in general. And so that's our asymmetric stretch. And it even shows a bit of the movement of the oxygen to maintain the center of mass. Okay. And that's the B2 vibration. So this is where those arrow pictures come from. So these are both stretches. We started with a stretch. We end up with a stretch motion, not the angle bend. Okay. So these are both stretching motions. The A1 stretch is the symmetric stretch. The B2 stretch, where one is stretching while the other is compressing, that's the asymmetric stretch. And it has a B2 symmetry.
So we should have one more vibration.
Yeah, we need one more. And so we're going to do this angle change. This is kind of a strange thing. We're trying to hold the molecule stationary, and we're just trying to decrease this angle. So I'm just trying to think of this half angle being decreased. And so I just put my arrow 90 degrees to the bond length. So the bond length doesn't change, just the angle changes here. And so we'll do this E, nothing changes. C2, it moves to the other hydrogen. And so what this also illustrates a point. The character table is going to move the hydrogens and these arrows to all of the chemically equivalent places in the molecule. So we could use this for NMR too, of the spins of the nuclei. But like if I'm moving the hydrogen, I just have to pick one hydrogen to move. And then if it's going to join with other hydrogens, the symmetry elements will move it around there. Like I didn't have to start with two arrows. I just started with one. And then that C2 moves it to the other one. And then the reflection moves it to the other one. And so on. So the character table will take care of all of the places that arrow will show up. Make sense? Okay. So that's why it's hopped over to the other hydrogen in the middle of the table, and then it stays put on the last column. And so if we add these together, we've got a couple of down arrows here on either hydrogen. And if we add them together, then that's what we have. So that's the bending motion for this molecule. And this tells us that the bending motion is A1 as well. Let's just verify that all these others are 0. Okay. So this one is the first column. C2 moves it over. But because we have a -1 on those two, they change direction. And so this down arrow cancels with this one. And this down arrow cancels with this one. And so we end up with no vibration for the A2 row. The B1 row, it just changes the different columns. See, the -1s are in different places here. Now the -1 is under C2 and under this, and it still results in no change in the molecule. And this one, the middle two are -1s. And so this one doesn't cancel. Look at this. Uh-oh, what have we got here? We've got an arrow, we've got 2 arrows down, and we've got 2 arrows up. Uh-oh. Yeah, that's rotation around X. So we've already identified that one, but that's what this is. So occasionally, like this case, you see that motion. If we did the hydrogens in that motion, then the molecule would rotate around X. And so that's not a vibrational picture. That's actually a rotational picture.
Which way is X exported on the Cartesian?
Yeah, so if we draw the molecule, it's a good question. So we have H, O, H. This is the C2 axis. Okay, and so that means that's the Z axis. Did everybody catch that? The highest order symmetry axis is the Z axis. And write that down. Whatever the highest n is, that's the z-axis. And then you draw your coordinates like this. You make a little Cartesian coordinate picture. So here is z aligned with the molecule, and you have this, and then we use the right-hand rule. X cross y equals z. So x is coming out front, and y is going to the right. Okay. So x is coming out to us, and so rotation around x would be those hydrogens rotating around that oxygen primarily, and rotating around the x-axis. Does that make sense? Okay, good. So like in benzene, you have 6 C2 axes, but you have one C6. The C6 is the z-axis. So let's just do that real quick. So we have benzene, and you can just draw it like Dr. Gross draws it, right? Forget the hydrogens. Now the C6 axis is coming out of the plane of the paper, and so that is the z-axis. And then this is x, and this is y. Okay?
Because I've always thought of it as the largest rotation axis. It's not necessarily rotation that defines.
Yeah, that's a C6 axis.
Yeah.
So we call it the principal rotation axis, the primary one, the principal symmetry axis.
So it is still based off the rotation thing.
Absolutely.
Okay.
So C6, we have C2s in a C6 in benzene, and so that's why I was making that point. We have lots of rotation axes in benzene. And a C3s too. Those are actually in the character table, C3 axes. But there's one C6 axis, and that's the Z axis. Now, why do we care about that? I mean, you could define the molecule however you want. Then you got to make your own character tables. Right? So these character tables are assigned that way. And so if we want to use these character tables, you got to get Z right, because that's how all of these are built. Okay. So that's why we're so picky about that, is because that's the way these character tables were constructed, is the z-axis and the C6 axis are the same in benzene or whatever. Acetonitrile has a C3 axis, and so now in some molecules like methane, it gets really complicated. So we'll talk about that one if we need to. For now, let's just move on. So let's do a molecular orbital, just to show that this works in other areas too. Okay. Those in undergrad who had me for undergrad have seen these notes before, but it doesn't hurt to go through them again. Okay. All right. So we have this is kind of a troublesome character table. This has an infinite number of elements in it. Okay. These rotational ones, I've simplified it by just including some of these blank columns, but there's an infinite number of reflection planes. There's an infinite number of C2s. Okay, so this character table goes on to infinity. All right, which is a problem if we were going to try to do that reducible representation for this. This is a classic trap for PChem professors. Okay, because you teach people how to do reducible representations, and then you make an exam and you're like, I'm going to give them an easy problem. I'm going to make the reducible representation for a diatomic molecule. And you give them that and they go to the deal and they try to calculate G, the number of classes, and G's infinity. And then when you do your things out here, all your little characters multiplied by each other, you divide by the number of classes, and it's infinity. And you got to divide by infinity. And I fell into that trap. And so many professors do. It's almost funny now, among us. It's like, yeah, I assigned a diatomic to the exam and had them do a reducible representation. And they looked at it and they're like, Dr. Williams, what do we divide by? So we're not going to be able to do the reducible representation for the homonuclear diatomics because of that infinite number of classes. So we're going to have to do this one by inspection. So we're just going to dive in and use the projection operator. So we're not going to do the reducible representation. We're not going to decompose that into the number and types of translations and rotations that we have, leaving behind the vibrations. We're just going to dive in and do the projection operator. And we see from water, right? We see from water that we're going to get the vibrations out of it, or we're going to get the molecular orbitals we'll see out of this projection operator. So we'll get the number and types of molecular either wave functions or molecular vibrations or molecular orbitals out of this. So here's hydrogen, dihydrogen. And if we were to just give you this molecular orbital where both 1s orbitals are in phase with each other, you see we draw them with the same shading, but notice that, you know, when we look at this, they're oscillating, they're expanding and contracting together in phase. And so if we just take this colored molecular orbital and we run it through the character table, what do we see? If we do an E on it, it's unchanged, but all of them are unchanged. So that's not going to tell us much. If we rotate it around the infinite symmetry axis around Z, we're not going to get any color changes, okay? So we get a +1. So the colors don't change, so we get a +1 on all these, and it matches all of those rows. And we're just going to do this for the single dimension rows. If we do a sigma V on these, so if I reflect this on a vertical reflection plane, the left and right side look the same because they're the same color. And so it's going to be one of these rows with a +1 in front of the A1, with a +1. It's not going to be a -1. This would indicate a color change. Okay. Inversion, if I invert this to the center of mass, so I take the value of this wave function right here, it's orange, and I go through the center of mass to the other side, it's orange. So that's a +1 under inversion. So it could be any one of those top two, but it can't be the second row because this had a -1 here. So we've narrowed it down that this wave function has the symmetry of A1G. We can go ahead and do the reflection rotation axis. If we rotate it, so if we rotate this point over, say, to here and reflect it through, we're down here, same color, so it's a +1 there. And if we rotate it around a C2 axis, you know, I pick this point, I rotate it around, I end up here, same color, so it's a +1. Okay. So you can see how you can use this. We're kind of using the projection operator backwards. We're taking an MO and we're seeing which row it came from. You see what we're doing? Yeah. And so if it came from that row, it has the symmetry of that row. And so this, we could label this wave function A1G. And that's what you need to be able to do. If I give you a molecular orbital, you should be able to go to the character table and say, okay, this is going to be an A1G molecular orbital. Let's do one that is, you know, the out of phase one where one 1s is expanding while the other is contracting. So this is that molecular orbital in hydrogen. Okay, it has a node in the middle. So we have, again, that C infinity. The first one doesn't tell us much. The reflection, because it's a reflection of vertical reflection plane here. Okay. The left side and the right side of the molecule look the same according to the way we've drawn it. So it's a +1 under reflection. But let's look at the inversion. So if I pick this spot right here and I invert it through the center of mass to the same spot on the other side, then we have a color change, so it's a -1, okay? And then if I do the reflection rotation, if I pick a spot here and I rotate it and reflect it down, I get a color change, so it's there. And so this is going to be produced by the A1U row, and so I would label this molecular orbital A1U.
So when you got to the inversion symmetry, could you have just stopped there?
Oh, yeah.
Yeah.
Absolutely, you can stop there. As soon as you can isolate it to one particular row, you're done.
Okay.
And you're like, it can only be this row. I just did the last two just as a check.
Right.
Mm-hmm. So that's the most reliable way to assign a molecular orbital symmetry, is to go to the character table and see which row it corresponds to. There are some problems with that when you get to the two-dimensional rows. And so we'll do the projection operator in a forward direction to assign those. Okay. Now notice too, though, this has Z symmetry. If you look at the Z axis, let's just plot it as if it's a number line. Okay, +1, +2. What's below 0, right? It's -1, -2, right? So that's the Z axis. Plus on top, minus on bottom. If I label this plus and minus, it has Z symmetry. You see that? It has a plus on the positive side of Z, it has a minus on the minus side of Z. If I operated on the Z axis with all of these, it would have this row symmetry. It'd be A1U. So the Z axis itself is A1U. If comparing this to the Z axis tells me that it's Z, then I know it's A1U. So I can look at the orbital too and compare it to the axes and say that looks like the Z axis, therefore it's A1U. Let's go back and do the same thing for this one. I circled Z squared. What if I plotted on the number line Z squared? This would be +1 plus 4, okay, because 2 squared is 4. This would be +1 and +4 because -2 squared is equal to 4. You see that they're the same sign on both sides of 0? Plus and plus, and so if this is plus here and this is plus here on the Z-axis, that's Z squared. Did you catch that? Okay, so if I square the Z-axis, all the numbers are positive. If I look at this orbital, all the numbers are positive. All of them are orange on top and bottom along the Z-axis. So the orbital lying along the Z-axis is all the same numbers, just like Z squared would be. And so it has Z squared symmetry. If I find Z squared in the character table, then I know the symmetry. Yeah, so that's the easiest. That's real fast. If you can just look at it and say, okay, that's Z squared, or that's X squared, or that's Y squared, then I've got the symmetry.
So if you use these techniques, I used to call it like, you used to get it right.
Yeah, you get it right. If you just say, oh, this is Z squared, then you've got it. Yeah. That's why we include those Cartesian parts to the character table so that you can make these associations. But let's use the projection operator to just a little bit about the energy level diagram. You know, this has a much larger box, and so naturally, if L increases, the energy will decrease. And then this has higher curvature. There's a node in the middle, so it's going to have high energy. So that's how we would put them in the energy level diagram, in terms of dropping and expanding the energies. So now let's do the projection operator for the 1s orbitals on hydrogen. So this is actually the equation for the projection operator. We have the projection operator for a particular symmetry, so that's going to be the A1, A2, B1, or B2. Operating on the wave function, so this will be like the atomic orbital wave function, the 1s orbital, and then we're going to add up all of those characters under each operation times that wave function. So this is just kind of telling you what we're doing. So the wave functions are the 1s orbitals on the hydrogens. These are the characters in the character table, and we're doing this for each row of symmetry. And so here we have the projection operator for A1 operating on the 1s orbital on atom A, on hydrogen atom A. And we have the character under E times 1s orbital on atom A. Okay? Then we have a +1 here, right? This is a +1, and so this is a +1. But this actually C2, sorry, we're doing the C2 next. It's this one. So this +1 comes down here to this one. But the C2 has moved the 1s on atom A over to 1s on atom B. So the C2 moves it over to atom B. Does everybody see that? Okay. Then the reflection in the XZ plane. Here's the XZ plane. So that swaps the 1s orbital over onto atom B. And we have a plus here, so it's a plus there. And then the last one is a plus again. And since it's the plane of the paper, that 1s orbital stays on atom A. And so we have the plus, so it stays shaded this way. This one is the same shading. We have another +1 on atom B, so it's the same shading. And we have a +1 on atom A, so it stays the same shade. Now there's a little bit about normalization. If you have two orbitals that come in and you know that your square of the wave function has to equal 1, then you need to divide by that by the square root of however many orbitals that you have. So 1 over the square root of 2 would be the normalization factor for that molecular orbital. But what you have here is 1sa plus 1sb. So if I were to draw this orbital, these would be the same shading. Whether they be shaded or open, they're going to be the same color. So they're going to be in phase, expanding together. Okay, let's do one that cancels out. So here we have the 1s on atom A. We do the C2, it jumps to 1 on atom B, and then we have a -1 here for this row. So -1s on B, a -1s on A. So we have a +1 on A and a -1 on A. So those cancel out. And a +1 on B and a -1 on B. So those cancel out. So there is no symmetry adapted linear combination of the hydrogen 1s orbitals that are A2. We have an A1 combination, but not an A2 combination. Notice we're just dealing with the symmetry connected elements right now. We're just dealing with the hydrogens. So these are symmetry adapted linear combinations of just those equivalent elements, atomic orbitals. Because if these hydrogens are equivalent to each other, they're going to oscillate together. They're going to have the same charge, the same potential energies, and so on. And so they're either going to oscillate with each other or out of phase with each other. This will have one symmetry, this will have a different symmetry. So we're just using the projection operator to see what those symmetries are. This one is A1, we figured that out. What is this one? So we've got to find it in this chart. So then this one, now we do the whole thing with the -1 when it moves over to this B, a +1 when it moves over to B, and a -1 when it stays on A. So again, these cancel. So the B1 row does not have this combination. So it's the B2 row, that's the only one that's left. So +1, the 1s orbital stays on A for the E operator. It moves to B for the C2, we get a -1. It moves to B with the reflection, we have a -1. And it stays on A with a +1 with the second reflection. And so now we have 1sa minus 1sb. See, the B's are both -1. And the A's are both +1. So this would be oxygen and the hydrogens here, where these orbitals, one is shaded and the other is not. So that's how we would represent that. One hydrogen is a different color than the other. So that's this motion. So here they are shown. So these are the symmetry adapted linear combinations of the hydrogen 1s orbitals. And that's all hydrogen has to use to bond with oxygen. Now, oxygen's super easy because we don't have to move it to any other oxygens. It's just by itself. So what do we have for oxygens? We have the atomic orbitals for oxygen. What is an s orbital? It's a sphere. It's x squared, y squared, z squared. So look at the character table. X squared, y squared, z squared, that's A1. So the 2s orbital on oxygen is A1 because it's symmetric in all directions. Positive and negative x are the same. Positive, negative y are the same. Positive, negative z are the same. So it's the same in all directions. So that's fully symmetric. That's top row. That's A1. But look at the p orbitals. Well, how do we label the p orbitals? Px, py, pz. So those are going to be x, y, and z. The px is going to be x, which is B1. The pz is going to be A1. The py is going to be B2. So now we can make a molecular orbital diagram with our oxygen atomic orbitals and our symmetry adapted linear combinations of s orbitals on the hydrogens. And this is the principle that you need to write down, okay? Wave functions of the same symmetry will interact with each other. So only those wave functions with the same symmetry will interact with each other. They will have a non-zero interaction. Okay. For the A1 orbitals, let's interact all three of those. Okay, we have 2s on oxygen, 2pz on oxygen, and the 1sa plus 1sb on the hydrogens. So if we connect the 2s with these, we end up with this picture that I got from Gaussian. You see that? There are no nodes. The hydrogens are expanding, and so is the oxygen 2s, and it's all pulsing. The electron cloud, this molecular orbital, no nodes, spread over the whole molecule, using the 1sa plus the 1sb plus the 2s on oxygen, all together in phase, interacting. But they don't have to be in phase, right? What if the hydrogens are shrinking while the 2s is expanding? Then we have a node. Okay, and so that's what we get next. So we have different colors for the hydrogens. They're still the same color as each other, but the oxygen 2s is a different color. Same A1 symmetry. So oxygen 2s shrinks away while the hydrogens expand. Hydrogens shrink away while the oxygen expands. We have this node where there's no change. And so we have this oscillation that's up and down in the molecule. And that's an A1 symmetry for that molecular orbital. Now let's mix in the PZ. So now we have a node that's very close to the center of the oxygen, and that's what we get up. This is a really ugly picture, okay, from Gaussian. It's way more complicated than we could have drawn. I'm going to draw this one by hand. So we have the 2pz here. So we have on the oxygen, we have a shaded thing on top and an unshaded thing on bottom, and then our hydrogens here are both shaded together. And so we have two nodes. We have a node here, and we have this really weird curvy node that goes like that. Okay, two nodes. And so we kind of see that here. It's just that Gaussian gave that those electrons as much freedom as they wanted, and they really expanded out over the molecule. But do you see how that's the hydrogen in phase with each other, and they're out of phase with the PZ orbital? Now, are there any other interactions between this? The answer is no, because we came in with 3 atomic orbitals, and we end up with 3 molecular orbitals. Okay, so if you come in with 3 atomic orbitals from the left and right side in the MO diagram, you end up with 3 molecular orbitals in the middle. Now let's mix this B2. So we've got this B2 for the hydrogen combination, and it's only going to mix with this B2 here, the 2py. And so they can mix in phase with each other, just like the pictures are drawn there, with one node down the middle, or they could be out of phase with each other. And this, again, these nodes are inside the molecule. They're really curvy. So that's the node. Looks kind of like a heart. Okay. So that's the node inside. And then we have a vertical node too still. So we have one node here and 2 nodes here. And the energy goes up as the curvature goes up. And you see these orbitals get very curvy. If they cross 0 a bunch of times, that's more curvature, that's more energy. And then lastly, we have the B1, which is by itself, the 2px. Now, I've rotated the molecule. Look at the hydrogens. I've rotated the molecule so that you can see that it's the px orbital coming out of the top and bottom of the water molecule. And it's by itself, and we would label that a non-bonding orbital. It doesn't have any interaction with the hydrogens at all. So it's not anti-bonding, and it's not bonding. It's just non-bonding. And then we have every one of these energy levels, and we have 8 valence electrons, 6 from the oxygen, 1 each from the hydrogens. And so we can just put those energy levels in there and fill the energy levels up from the bottom. And now we have the highest occupied molecular orbital here. This is the more. So that non-binding orbital is the highest occupied molecular orbital. So that's using the projection operator to generate our symmetry adapted linear combinations in hydrogen, and then combining them with the oxygen atomic orbitals to make the molecular orbital in water. Molecular orbital energy diagram. Let's go ahead and do this projection operator for ammonia. It's a little bit more complicated molecule. Now, if you'll notice from the character table, I've expanded this quite a bit. In the character table, it says 2C3. Well, in order to show where that 1s orbital goes, I need to split that apart and show it's the C3 and the C3 minus 1. So if I'm sitting on this 1sa, if I do a C3, I end up at 1sc. If I go the other direction, I end up at 1sb. So I can go from from A to C or A to B, depending upon which direction I do the C3. The same with the three reflection planes. And so I went ahead and took this 3 here and split them into the 3 reflection planes that each contain an NH bond. So we have the A1, A2E projections, we have the characters, and then we have the wave functions, 1SA, 1SB, or 1SC. And so let's go through these rows. We have 6 elements in this thing. Let's do the A1 here. So the A1 row, the E gives me a +1, and the orbital stays on atom A. The C3, I rotate it sort of towards the back, like clockwise from the top. Like if I have a handle on the top, I turn it clockwise, and it shows up on atom C, right? So I moved 1sa, now I'm on atom C, and I have a +1. And if I move it the other direction, I end up on atom B, and it's a +1. If I reflect, and so this is the first reflection plane, it stays put. If I reflect it in this one, then it goes over to C. And if I reflect it in this plane, it jumps over to B. So does everybody see the reflection planes? It's just each of the NH bonds is a reflection plane, and I'm hopping that orbital over to the other chemically equivalent spots on the molecule. And because I'm on the A1 row, they're all +1s. So if I go through this, I have a 1sa and a 1sa, a 1sc and a 1sc, a 1sb and a 1sb. So I have all of them survive. And so this is going to be my wave function. It's going to be 1sa plus 1sc plus 1sb. Okay, so this would be, that N, H, 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 where they're all the same shading. That's that A1 molecular or symmetry adapted linear combination. If I do the A2, you can go through this and see where the minus signs are. They're on all the reflections. And so that cancels everything out. So there's no combination of the 3 1s orbitals that gives me A2 symmetry. Let's jump ahead to, since we're running low on time, let's go ahead and do E. So now we have these different numbers here. So on the E operation, it's multiplied by 2 on the 1sa. Then when I do the rotation, I get a -1 on the 1sc, and I rotate it the other direction, it moves to B, and I have a -1 there. And then because I have 3 zeros here, the reflections are all canceled out, okay? And so what's left is 2 times the 1s on A minus C minus B. So what does that look like? That means the 1sa is sort of increased in size, and these are shaded. So there's a node now. You see the node? And so this is this one expanding, and these two contracting, and these two expanding, and that one contracting. And so this is the picture that we see right here of that one. It's 2, well, it's right here. I've written it out. 2, 1sa, and then change sign means change color on 1sc and 1sb. So we were able to generate that molecular orbital picture, at least with the hydrogen pieces, in using the projection operator. Now that gets you one of the pairs. The other pair is this one. This is the other of the degenerate set. That's an E, so there's two combinations. And the only way I can think of to generate this is to say, well, I use the 1s twice, so I use it 0 here. So I have 0, 1sa, right, plus 1sb minus 1sc. So notice 1sc and b are the same here, so they're going to be opposite here. And I used a twice, and I use it 0 times here. The other way to think of this is look at the nodes. This node is here, and in degenerate sets, their nodes are 90 degrees to each other. So this node is 90 degrees to it. Okay. So the projection operator is real easy to get one of the degenerate sets. And so to get the other one, you just have to think it through and say, yeah, if I used the 1s orbital in atom A twice, sort of made it twice as big here, I'm going to use it as 0 times in the other set. And if these guys are together in phase in the first set, they're going to be out of phase in the second set. The same thing works with vibration. Okay, so looking top down, oops, we could have done the arrows in this projection operator, and we would have a twice as big arrow on this hydrogen, and a single arrow on this one, and a single arrow on that one. And so notice this motion is going up and down. The degenerate set would be motion that's going to the right or the left. And so this would be no arrow on that hydrogen, an up arrow on this hydrogen, and a down arrow on that hydrogen. Notice how this motion is moving left and right, and this motion is moving up and down. The math is the same whether you're using arrows or atomic orbitals. And you get the same results here. So this, if we label this RA, RB, and RC, then this wave function is equal to 2RA minus RB minus RC. A is increasing while B and C are decreasing. So this is pretty cool that there's nothing that ties the projection operator to vibrational motion or to molecular orbitals and atomic orbitals. It's the molecule. It's the symmetry of the molecule. So everything that molecule does will be in that character table. And the math works out the same. With threefold symmetry, you get 2 of one minus the other 2, and then you get nothing of that one and the opposite of the other 2, whether it be arrows or orbital shading. And it's amazing. The symmetry of these things and how it applies to vibrations or vibrations of the electron cloud fascinate me. The math is so beautiful, no matter which piece you're dealing with, that you would have these same combinations. It works with angles too. An expansion of one angle twice as much as the other 2 shrinking, you get the same for the deformations. It's really pretty cool. Once you kind of get a feel for it, then you can jump to the answers pretty quickly. Okay, so I'll stop there because we're out of time, but hopefully you were able to follow it. If not, there's the video. Okay.